Hi again. Welcome to the first video about solving simultaneous linear equations in algebra. In this video we develop the basic graphical technique for obtaining the solutions to the two given variables and see how the graphs can be used in practical situations. A linear relationship is a relationship between two quantities or variables in which change in one quantity affects a change in the other quantity by a fixed amount. There are many such relationships that we come across all the time. For example, we take the distance equals speed times time relationship. So if we say that our speed is 3 meters per second, then we can write distance is equal to 3 meters per second times the time we ran for. So in symbols, we can write d for distance equals 3 for the speed times time. If we're travelling or buying things from overseas, we might be interested in exchange rates. The US dollar is equal to about 69 cents, 0.69, times the number of Australian dollars that you've got. So if you've got $100 Australian, we're going to get $69 American at present. The cost of folders for a school is equal to the cost per folder times the number of folders that we buy. We might be comparing two mobile phone plans. One plan says that we're just going to pay $80 per month for a long time. The other plan says that we can buy the phone outright at $800 and then just pay a prepaid at $30 per month. So we might need to find when the plans had the same cost, which we refer to as the break-even point. So we will need to solve those two equations together to get our answer. To start learning our technique for solving two linear equations together, and we call that simultaneously, we refer to an example where we are just given two equations. There's no descriptions about what the variables are, and we have to find their point of intersection using graphs. This is a fairly common one. The two equations we've been given are y equals 3x plus 1 and x plus y equals minus 3. So the first step is to draw up the axes that we're going to need and label them x and y. Second, we plot the points for the first line. So when x is equal to 0, y is equal to 1, and in the first line, and when x is equal to 1, y is equal to 4. So we note those 2 points down, and then we draw in the line that goes through those 2 points. We repeat that exercise for the second line and plot the points. Now again, when x is equal to 0, y equals minus 3, so that's down the bottom. And when x is, say, minus 2, just pick a number that fits the axis. So y is going to equal minus 1. So we plot that point. And then draw in the line that we need. So we've now got our two lines waiting for us to do things with. Because we don't know what the variables mean here, really the only sort of thing we can do is to identify the point of intersection. So we go to the point of intersection and we find that the x value is minus 1 and the y value is minus 2, so that's our point of intersection which we would write down. A much more interesting situation is when the relationships being modelled by the equations are real events, such as the mobile phone plans we mentioned earlier. Now another example might be, Jim runs at 3 meters per second in a 100-metre race against Sarah, who gives him a 10 metres start. Sarah can run at 4 meters per second. She's a little bit younger than Jim. We can develop equations for the distances covered by the two champs. Jim has got his distance, which I've left dj, is equal to his speed, 3, times the number of seconds he runs for, t, plus the 10 seconds that Sarah kindly gave him a start. Whereas Sarah, ds, distance for Sarah, is equal to her speed, 4, times the number of seconds she runs for, but she started off 0. We go through exactly the same steps now to draw the two lines. For Jim, when we're starting, t equals 0, he's on 10 metres, so we put that point in, and then we go somewhere along the line to say 20, and we say, well, 3 times 20 seconds plus 10 is 70 seconds, so we put a little ring around that point and we join those two up. For Sarah, we do the same. When t is equal to 0, we have the distance is 0, so we put a ring around there, and again go to t equals 20 again, just as easy. 4 times 20 is 80, so there's a little ring around Sarah's 80 there, and we join those lines up so that we can see the blue line is Jim and the red line is for Sarah. So now let's ask some interesting questions. First of all, who came first? Well, Sarah's red line is the one that hits the 100 metres first, so the arrow shows Sarah came first. Second question, how many seconds separated the pair when they finished? Well, we can see on the top there that Sarah finished in 25 seconds and Jim finished 30 seconds. So they're nearly dead heated. It's only 5 seconds difference. The third question is, how far was Jim behind when Sarah reached the 100 metre mark? Well, the little arrow shows that Sarah was at 100 metres and Jim was down there at 85 metres. Again, almost the same, just a short 15 metres difference between the pair. And finally we ask, after how many seconds did Sarah pass Jim? Well, we go to the point of intersection, which is the break-even point, and we go put an arrow down, and it took Sarah 10 seconds to get to Jim and pass him. She's a pretty good runner. So to recap on our methods for solving two equations simultaneously using graphical methods, first you have to identify the two equations that are needed. They will be linear. Sometimes you're given them, sometimes you're not. Second, draw the lines one at a time on a set of axes. Start with x equals 0, it's nice and handy, easy to substitute, to find the first point on the first line, then try a second x value which fits the context, then repeat to draw the second line. Third, be as accurate as you can so that your answers to the various questions are accurate. There's no point in trying to do this in a slapdash way. Take your time and do it nicely. And fourthly, appreciate the graphical method can raise not just answers to the break-even point or the point of intersection, but it can also talk about a range of really interesting and relevant questions about a particular problem. So you now have the steps to graph a pair of simultaneous equations to answer such questions as, where did the lines cross? Or what is their point of intersection? Or some other interesting questions. Hope I have helped you to clarify the approach. Thanks for watching this video. In the next video in the series, we look at using algebra to achieve the same result. That approach is used in advanced maths classes. Hit the like button and subscribe if you haven't already. Also go and do some questions in Simultaneous Equations Test Yourself 1 on my website at drjsmaths.com. Add a comment below and send me an email if you have any questions. Good luck. See you later.